Uh, cool. Hi. Good afternoon. It's great to see so many of you here today. Thank you for being here. I know there is like a post-lunch carb slump, but to commemorate this moment, I'd really like to take a selfie for my socials. So, yeah, you're all going to be in it. Who can I get a whoop whoop? Woo! Oh, come on. It's after lunch. I know you can do better than that. Cool. Thank you. Cool. I'm sure the ones, those of you on the first row are kind of regretting your decision, but yeah. So yeah, thank you for that. Let's get straight into it. I'm Annem. I am a cloud engineer at Charlotte Tilbury Beauty. Fun fact, my name in Turkish literally means my mother. I go to Istanbul a fair bit, and that does get a few weird looks at border control. But yeah. I started off my career in the Department of Transport as an Azure engineer, so we were moving from on-premise to Azure. I moved to consultancy, worked with a variety of fintechs around London, met some great people along the way, and that was a really great experience. I decided that it was a really valuable stint, but I wanted to try product-led development again after speaking to one of my mentors. And I found myself at Charlotte Tilbury last October, which feels really full circle again. I definitely see our developers as our stakeholders. Making the platform more secure, more scalable for them generates into revenue for us. And in these efforts, I also set up an infrastructure guild to kind of share knowledge across the team. It's great to be somewhere that considers DevOps to be an integral culture rather than just a traditional infrastructure request team. The people really make the place, so honestly, I'm really enjoying my time there. I thought we'd start off with a really quick quiz. So there is a prize at stake. So I am offering our flagship product, Charlotte's amazing magic cream, the best-selling moisturizer for a few years. The first person to answer correctly wins. Just put your hand up. The question is, what is idempotency in the context of infrastructure as code? Cool. Yeah, basically that's the right answer. And we'll get into that more deeply. But yeah, do find me at the end and I'll make sure that you get your magic cream. If nothing else, I've emphasized the importance of moisturizing to you all today, if that's the only key takeaway that you get. Cool. So not too long ago, I promise you, when I started off my career in cloud computing, the closest my team were getting to infrastructure as code was caching credentials in a Microsoft PowerShell IDE, writing the PowerShell scripts that we needed in the command line to create instances and resources in Azure. It's pretty inelegant and kind of defunct now. We then discovered Azure ARM, Azure Resource Management, and blueprints, which you write in some flavor of JSON, and you keep as templates in source control. But it's still not readable or easily understandable at first glance by everyone. So that brings us kind of to Charlotte Tilbury. So at the time, at Charlotte Tilbury, they were exclusively using only CloudFormation for both application and infrastructure deployments. CloudFormation is AWS's own IAC. It only works with AWS resources. And similar to YAML, we write resources in a nested way, with a CloudFormation stack representing a collection of individually defined resources. And at the time, their only CI/CD tool of choice was CircleCI. But this was set up in such a way that our application and infrastructure deployments were both running in parallel and dependent on each other. So each time we would run an application deployment and pushing code up, the corresponding infrastructure code would also run and go through each stack to see if there are any changes. But as a fast-paced beauty organization, where things are always happening. We have something quite unique in that we offer 24/7 support, and so we have to be really on the ball at all times to making sure that we provide the best experience for our customers. Now, say, for example, an incident occurs at 3 in the morning and an alarm goes off. The appropriate course of action at that time would be to manually update the scaling values in the AWS GUI from 2 to 8 to 8 and 16 of a service. And it makes sense just to do this manually in the AWS portal. And this then bypasses the alarm. The next day, after the incident post-mortem, we then decide we want to revert the values back. But there's been a gap between those values being manually changed and up until the post-mortem. And they've been scaled out and they've not reverted back. So even when another engineer is editing part of the code base and pushing up their changes, CloudFormation won't recognize there's been a change and there's drift, and it won't revert those values back. So it won't recognize there's been a change in the state, and it won't revert those values back to the original values. That brings us on to this scary thought, which is that at any given time, whilst we were using CloudFormation, there would be services declared in CloudFormation that doesn't match what exists in the actual state. And that can be a lot of drift that goes undetected, and we're not sure where it exists in what stacks. So while CloudFormation does have some sort of drift detection, and is relatively good at enforcing the configuration declared in the code, it does have flaws. So drift detection is done manually, and to fix drift, it can require manual intervention as opposed to just force applying the CloudFormation code. And if something is changed in the infrastructure manually, like our example before, certain CloudFormation resources won't be detected to have drift and won't go back to their original values on subsequent runs. And it's not always clear what resources and services that we detect will be flagged up for drift and what won't. With Terraform, it's harder to drift. So even on the next run with our last example with our on-call engineer, even with manually updated values, Terraform recognizes there's been a change between the AWS portal and the Terraform state definition. And it will revert the values back to what's in the state, meaning that our state is always taken as our single golden source of truth. So here's where we get deeper into idempotency. Terraform is also idempotent and declarative. So pretty much in the saying, declarative code is describing an intended goal rather than the stage to reach that goal. So the ordering of blocks, resource blocks, and the way they're organized isn't particularly clever. Terraform only considers implicit and explicit relationships between resources when determining an order of operations. So here we have an example of 2 different deployments of the same resource, AWS CloudTrail. CloudTrail is an AWS resource which logs and audits events and activities in the portal, usually used kind of for security, but SecOps and auditing. And as well as the actual CloudTrail resource that we're defining, we also have an S3 bucket. We're also creating a CloudWatch log group as well, which we need. And we can define those resources in any order in Terraform, and Terraform still knows what we're creating, and it will order it in the apply process when we're creating our resources. Unlike with CloudFormation, where we have to write each resource in a nested way, similar to how we write YAML, CloudFormation stacks have a specific template that we can't veer from, otherwise it will throw an error. Now, idempotency is talked about a lot with Terraform, and what it really means is no matter how many times you run your infrastructure as code and what your starting state is, you will end up with the same end state. A natural consequence of this kind of imperative, of this idempotent approach, is being able to run the same code over and over again without any side effects or changes to the resources being managed. And in the context of Terraform, what we're defining in Terraform is exactly what is being deployed. And this is really important with CI/CD tools because they can be run to change configuration and to also verify that your configuration actually matches what we want. So we can continuously run Terraform apply, whether manually or in a CI/CD job. And if your configuration matches what is actually defined in your plan and state, it won't actually change anything. So for our migration, we wanted to emulate best practices from Terraform and ensure that our code was as modular and flexible as possible. So for us, this meant defining each CloudFormation stack as a Terraform module. Now, this was pretty easy and seamless for us because we had already defined every CloudFormation stack as a service, like CloudTrail, as you saw before, or AWS Event Bus or S3. Now, these modules should be reusable, which means that we can reference common resources across other areas of our infrastructure code base. Because we've already defined the resource with the parameters that are in line with Charlotte Tilbury's security engineering practices. So, for example, we have a policy that enforces a default limited retention policy on our S3 buckets, so we don't want to be keeping data in our buckets for more than 30 days, and we want AWS to delete it afterwards. So that's in line with Charlotte Tilbury's engineering SecOps practices. So we have a fully made module already for S3 that we can use and rinse and repeat across every other area of our code base. But if we have an example where we don't want to apply that limited retention policy, we can also add other non-static parameters and properties to that module where we're using it. So we have a more bespoke approach as well. But if we just want to rinse and repeat that same module, we can also do that as well. And it'll always be in line with our engineering practices. Cool. So up until this point, I had only used GitHub and GitLab with Terraform, which is where we write bespoke YAML jobs to plan or apply Terraform in steps that we define in our code. And this also means steps to download Terraform, logging into your chosen environment before deploying. And this is all before being able to read the plan that comes in the output before we apply the changes and when we push those up to the source control. So unless we write some scripts to be able to format that plan output, it can come out in a way which isn't very user-friendly. I've had issues before where plans have failed because they've been too long and GitLab hasn't been able to pass that plan. There can sometimes just be too much riding on it. And that's part of the reason why we decided to use HCP Terraform, which you might know better as a Terraform Cloud, which is HashiCorp's CI/CD tool of choice. So whilst we as a platform team look after the shared infrastructure, we do emphasize a DevOps mindset culture across the team. So each squad looks after their own services, and that's both application and infrastructure code as well. So that means engineers less experienced in infrastructure also use Terraform, and sometimes for the first time as well. We decided to use HCP Terraform as our chosen CI/CD tool for infrastructure because it takes care of that steep learning curve and inaccessibility, which can be present when running Terraform in a more generic CI/CD tool like GitHub Actions or Jenkins. And a well-formatted and laid out Terraform plan with the changes really clearly highlighted and color-coded were empowering for the junior devs in our team. They were able to put through small single-line changes themselves, like unblocking or blocking an IP address or amending a parameter in an alarm. It's easily isolated. It can be seen as something not scary or something it won't break other changes, and it's isolated. And that helps build their confidence in Terraform as well. And it meant that we, the platform team, were cultivating a high-velocity infrastructure team, which benefits all, shares knowledge, and it minimizes bottlenecks for us as well. So the migration itself, now we've set the scene. So for me, the easiest way to start writing a Terraform module was by looking at the CloudFormation stack, finding recognizable resources and starting there, and as well as cross-referencing the AWS HashiCorp provided documentation when needed to find other mandatory parameters that we might need. We can successfully test that the module works first by calling the Terraform module we've just created in the chosen environment. And of course, we started with pre-prod first and took it from there. And then when we run the Terraform plan in the Cloud GUI, we know we've been successful when the plan declares all the resources that we've defined in our module configuration. We don't want to hit the big red button to apply there first. Rather than creating our resources, we want to import them. So why would we want to import our resources rather than just create and apply them? So the resources already exist. CloudFormation created them. But Terraform is unaware of what exists outside of its state. So we would end up with duplicate resources, or it would just fail upon applying, saying that you already have these resources with the same names that exist in AWS. So where we have S3 buckets that contain tags, metadata, and assets, we want to transfer them from the CloudFormation managed policies to be Terraform managed to be able to keep the assets in them. Previously, the import command was only available in the command line. I've messed up before, and you do not know pain until you have to manually import a Terraform resource line by line and find the unique identifier, which only exists in the plan itself, and run it against Terraform import. But the Terraform import block, it's similar to a resource block, and where we reference resources that exist outside of what is known to our Terraform state, like our CloudFormation infrastructure. We can then preview the import in our plans before it's created and define it in a CI/CD job as well. And once imported, Terraform tracks the resource in the state file. We can then manage the imported resource like any other, update its parameters and properties, and destroy it as part of a standard resource lifecycle. So this brings us on to our case study. So one successful case study that we did recently was on our assets repo. And in this repo, we had defined a CloudFormation stack which created an S3 bucket and contained images and thumbnail and fonts which were used in customer emails. So this repo was quite small, but very impactful because it meant that we weren't, for some reason, at some point, we weren't loading these fonts and some thumbnails in emails which customers were getting. And we triaged the issue to this repo. All it needed was some additional cause configuration, which is configuration that we just used, point to the S3 bucket to be able to pull those assets in there to these emails. That's our fragrance launch. If you don't know, look on the website. And as we needed to add additional infrastructure code, and this was a CloudFormation template that was due to be migrated, we decided to just do the migration and add the additional cause configuration in Terraform all in one go, rather than just doing a quick patch fix. So how we did this? We created a module for the assets repo, and we wrote the resources that we were intending on importing in first as import blocks. We then defined empty string variables as we were adding these in Terraform Cloud in the console for each environment workspace. This picks up environment-specific variables here, so we only need to define one main configuration in code. But we have multiple variables which aren't static. This fits in really well with dry, don't repeat yourself best practices, so we're not repeating code that we don't need for each singular environment. So after calling the module block, adding the source, which is a relative path to the module, we can then add the import statement for the existing resources. And as the assets S3 bucket already exists, we can define this as a data block, which is a reference to an existing resource, including the name of the bucket that we're referencing being the exact name of what the bucket is currently called. We can then add the rest of our import statements. Now, our import statement has two arguments: what resource we're importing to, and then the ID of the existing resource. We want the target to reference our module name, adding the Terraform identifier, which is defined in the module, and the ID is the exact existing name of the resource. We can then test this either by running a CLI command locally, which triggers a HCP Terraform run, or we can just push the changes to our branch and see the results in the console. And the way we know we're successful is when the Terraform plan picks up that we're importing our resources rather than creating them. And you can see there is a clear distinction between importing resources and creating them. But in this case, we're also creating resources as well, so we needed to add the cause configuration. pointing to the assets in the bucket that we're importing. So we have the flexibility to import resources, but also to add extra properties and parameters as needed. And Terraform would create those properties in parallel in the same run, as well as importing the resources that we need as well. Importing resources rather than deleting and recreating is especially important in this context because we don't want to delete any images or fonts or assets which are stored in the assets S3 bucket that we're bringing into the state. We also had a deletion policy on the bucket, including its contents, so we kind of have that fail-safe, more on that in a bit. And before applying the imports, one thing to note is to add that deletion policy to your CloudFormation stack. Otherwise, when you go to decommission the CloudFormation stack, you may well delete your resources as well, which is something that we definitely do not want. So now we want to tie up any loops. Now we've imported our resources. So we now have no need for the CloudFormation stack. Those CloudFormation resources are parallel to Terraform, and we don't want two different tools governing the same resource. So we can safely decommission the CloudFormation stack. But first, we want to comb over our Terraform resources, check the names, policies, bucket policies to ensure everything matches what was defined in the state. And then we need to check that all the resources have that appropriate deletion retention policy, and then we can nullify the CloudFormation stack. And once this is done, we can remove the resources from the stack, and CloudFormation will remove those from its state when we push up the empty stack. And now it's only our Terraform resources that exist, and they are the single source of truth. And now we've imported everything, we can safely delete the stack as it is now empty. So these are some things to keep in mind if you are considering moving from CloudFormation to Terraform. So one pitfall that we did face was we found that the ID of the import block for resources differs for each, and it's not always clear what it is. For example, for an S3 bucket, the ID to import, like we said before in the example, is simply the name of the bucket, whereas for a CloudWatch resource, it could be the path of the logging group, or a unique string that concatenates the ARN with the region. Check the documentation now. As far as I know, this has now changed, so I think in the last few weeks on the AWS provider documentation, so you can see what an import block is, and it gives you an example of what your target and your name and the ID is as well. And with the plan, if you're not going through with a fine-tooth comb and checking all the resources, sometimes you can miss changes in the configuration. Again, with the assets repository, when we reached all the stages of the import plan, the root 53 DNS record that was declared in the plan was changing upon import. But Terraform just flagged it as being imported, but when you expand on the resource, the actual string of the DNS record was changing, and it was adding .s3 or something. It didn't throw an error, but we realized that the ID of the import block for the DNS record was concatenated wrongly. So it's always worthwhile before you hit that apply button just to go through, check and double check. The last one was pretty much all on me. I didn't realize that by deleting the CloudFormation stack, AWS believes that the now managed Terraform resource still belongs to it. But however, we need to include that resource deletion policy in the CloudFormation, in the empty CloudFormation stack. And that means that it won't delete the resource attributes itself. It will just remove the stack, so it will disappear from the AWS CloudFormation console. But luckily for me, I only got as far as pre-prod before I realized that our assets bucket had no policy attached to it, so don't do as I did. And some key takeaways. AWS CloudFormation generally works really well in a single CSP environment, which we were. But with the way our infrastructure was set up, where we had our infrastructure and application deployments kind of dependent on each other, it meant that migration, as we were adding new services in and our platform was getting bigger, it meant that migration was the next natural move for us. HCP Terraform really helped us with this, especially with a team like ours where we have so many developers with so much varied experience, some whom have never used Terraform before, I think that Terraform Cloud really provides a really user-friendly experience for those. It empowers them to make changes themselves. So it means that we, the infrastructure team, can focus on the good stuff, making our platform better, more secure, and scaling it. So cool. If you've gotten to this point, there's no Q&A, but if you'd like to find me at the networking reception, even just to say hi, or if you have any questions, would love to speak to you. If you don't want to, then yeah, reach out on LinkedIn if you'd like. There's my QR code. Prize winner, come find me and I'll make sure that you are united with your magic cream. And yeah, please do connect with me if you'd like. And thank you all for being here. It's great to be on stage with you. And thank you. Big shout out to HashiCorp and Claudia for making sure that everything ran so well today. And big shout out to Charlotte Tilbury's engineering team getting this presentation across the line. It was a huge group effort. And really appreciate that, all the work that everyone put in to help me get to this stage. So yeah, thank you ever so much, and I hope you have a good rest of the afternoon.